In 11.4, we're doing the opposite of what we did in 11.3. We use this theorem, de Moivre's theorem, to take complex numbers and raise them to a higher power. Here we're doing the opposite. We're taking the roots, like a square root, cube root, fourth root of complex numbers, using the same theorem. So your problems will look like this in 11.4, all right? And I want to be clear on the first part here as to why this is what we're going for, okay? The cube root of 8i would look like that, okay? So we're looking for this complex number z that's the cube root of 8i. If you were to take this and raise both sides to the third power, the cube root and the third power would cancel, and you have 8i equals z to the third. Okay, so that's what we're looking for. And just to illustrate how this is different, in 11.3, we'd take a complex number, okay, and we'd look for this. Okay, what is that complex number raised to the third power? Notice the cube is now over on the other side. What complex number raised to the third power is 8i? Okay, well, the very first thing we need to do is, just like 11.3, we need 8i, which is right up here. We need 8i written in polar coordinates. Okay, now this one falls right on the boundary point, so it's not too tricky. I can just see that the distance from the origin is 8, and theta is 90 degrees. Okay, so then I would say on the right side, I could rewrite 8i, 8 cis 90. Okay, so z to the third power is 8 cis 90. And over on the left, I'm going to fill in here that I'm looking for r cis theta to the third. That's essentially what I'm after. For a complex number, what value for r and theta, when I raise that number to the third power, will it equal this? Which I've just shown on my little diagram over here is 8i, 8 cis 90. Now here's where de Moivre's theorem comes into play. This stated that when a complex number is raised to a power, this is r to the third cis 3 theta. Okay, this is really the key right here to get both of these sides in this matching form. Because now I'm all set up to find r. Notice how those two parts kind of correspond. Okay. For 8i, r to the third is 8, and then 3 theta is 90. Okay. R to the third is 8, 3 theta is 90. I'm after r and theta. Okay. And it's important to be clear here that 8 and 90 degrees, that's z to the third power. Okay, that's r to the third and 3 times theta. So then I take the cube root, and I get that r is 2, and then I divide both sides by 3, and I get that theta is 30. Okay? Now, I'm not quite done, but what this does tell me is the first root is 2 cis 30. Okay? 2 cis 30 is our first root. Now, I'm not quite done. Okay? It's a cube root, so I have 2 others to find. Okay? And the key is right here. I need to think about multiples of 360. Okay? Coterminals. Coterminal angles come up here. Okay. But the very next thing I did for this equation that was 3 theta equals 90 is I divided by 3. So when I get down here and I got my first angle as 30 degrees, I no longer need to look at multiples of 360. Rather, I take 360 and divide by 3. I need to look at multiples of 120. Okay? So in addition to 30 degrees, I add 120, 150. That's an angle that I need. I add it on there one more time. 270 is an angle I need as well. Okay? So 2 cis 30, that's root number 1. 2 cis 150 is root number 2. 2 cis 270, that is root number 3. Okay? And that's it. I have my 3 roots. Now they're still in polar form, so here's one other thing that the problem could ask you to do. And I'm going to do it over on this slide right here. This is the formula. A lot of times people don't find this formula to be helpful, and they just go off of the examples. But that's the technical formula. One thing I do want to add to this is it's totally possible. Remember we had 2 cis 30. If we wanted to put those back into standard form, remember this is shorthand notation, and what it's saying is that the real component of our complex number is 2 times the cosine of 30. The imaginary component is 2 sine 30. Okay? So if this wanted me to put the answer for Z1 back into standard form, I'd go to my unit circle and I'd have to evaluate what's the cosine of 30 degrees. That's square root 3 over 2. Very first thing I do when I put in square root 3 over 2 for cosine of 30 is I multiply it by 2. So the real component is the square root of 3. And I do the same thing for the imaginary component, but now I substitute in for sine of 30, which is a half, times 2 is 1, and I'm just left with I. So square root 3 plus I. Notice I'm back in that A plus BI form. So that's back to standard form. Okay, so really this is what I'm looking for in terms of a root, okay, one of the cube roots of 8i in standard form. Remember the other 2 roots that we had were 2 cis 150, and the third root that we found was 2 cis 270. By the exact same process, okay, we could take this and write it out. 2 cosine of 150 plus 2 sine of 150 times I. Okay, evaluating each of those components. Okay, I'll leave you to do that one on your own. Okay, that's just a unit circle. You'd have to substitute in the values for cosine of 150 and sine of 150 and simplify. Okay, that would get you the standard form of the second root. And last but not least, I'd have 2 cosine of 270 plus 2 sine, see if I can fit it in here, of 270 I. Okay. Same thing there. Okay, evaluate cosine of 270 and sine of 270. You'll also find those values on the unit circle. Okay, so see if you can finish off this example with putting those back in standard form. And last but not least here just would be another example, just to remind you how to get you started on this one. What this is asking is what complex number to the fourth power equals negative 16. Okay, graph it. Start by finding r and theta. Okay, and go from there. Okay, but that's how to set that one up.